All right, everyone. Let's go ahead and get started. All right, so we have quite a lot of announcements, so please pay attention for the ones you haven't heard before. First things first, Cyber X AI Symposium. So if this is your first year with us in cyber, something we like to do at the end of the quarter is have a symposium where we get to present what we've been doing in Cyber Academy or Cyber Lab, PDR. So this is going to be Tuesday, week 10, which lands on December 2nd, 6 to 8 in the Hmong Auditorium. So yeah, you get to see all the cool work that we've done here in cyber and also in Cyber AI, our good friends there. Please RSVP. This is required if you want to get food. We are ordering food, but you need to fill out the RSVP because, well, okay, if you want details, you can ask it later. But yeah, please fill this out, l.acmcyber.com/symposium. And I guess we set a deadline, huh? Hell, that's like in 9 days. Just do it now. And yeah, if you want to present a cool challenge at symposium, like maybe something you did in PBR, yeah, just let someone an officer in like I guess academy or lab or whatever, just let them know. And yeah, I guess this QR code should also take you to the link. Everyone have that link at least. You don't have to have finished filling it out now, but yeah, all right. Cool. All right, so this week, some announcements. Tomorrow, we have another eCTF workshop. This will be on Pwn, or binary exploitation is the long name, presented by our very own Ryan over there. So that's tomorrow, 6 to 8 in the Engineering 4 Maxwell room. And then on Wednesday, we have Cyber Lab as usual. Alec will be talking about the recent AWS outage, what was going on with that. And then this Saturday, we've got PBR again. We'll be doing Buckeye CTF. This is hosted by OSU. Buckeye has been historically a very good CTF, at least in our opinion. So yeah, it'll be a good time. So same place, Engineering 4 Tesla room. And yeah, if you want to join us for lunch beforehand at 11 a.m., we usually meet at the Nev Crosswalk, and then like somehow we decide on a place to go, and then we go get food. Yeah. Okay, so this one we've announced it before, but in case you forgot, next quarter, some cyber officers are going to be teaching an E1 course. It'll be Engineering 1 MD, Malware Defense. So it'll be on Thursdays, 12 to 3. You can enroll at this link, l.acmcyber.com/E1. Yeah, it'll be a cool class. I guess if you're a freshman and you're doing CS32, it technically conflicts with it, but you know, you can just watch David A. Smallberg on your own time with the videos. So yeah, you can still come.
I'll also add right now, there are no restrictions. So if you're not an engineering major, you can enroll right now. I don't know how long that's going to be the case. So enroll earlier rather than later if you are not an engineering major.
Yep. And then something that we may or may not be trying, I guess, but there's this thing called CCDC, Collegiate Cyber Defense. It's a little different from, or it's not a CTF actually. This is more like blue teaming, I think. Allegedly, it's like the college version of Cyber Patriot. I did not do SciPat in high school, but I guess people who did, they say it's like similar. So if you are interested in potentially doing this, fill out this form at l.acmcyber.com/ccdc-interest. So this is just sort of to gauge like whether we have enough people to form a team. And if so, we'll try to go ahead and get that moving. The competition will be next year, February 7th. This is actually the planned LACTF date, which is rather unfortunate, but if you're interested in doing it, don't let that stop you. So yeah, and QR code as well. All right, everyone done with that? Okay. And lastly, quick word about socials. So yeah, we've talked about Cyber Potluck before. Thank you to everyone who RSVP'd. If you want to come and haven't filled this out yet, please do that. A new one we're announcing is the Cyber X. Oh, that's a lot of people. Okay, so it used to just be Cyber X ICPC, and then I guess Cloud and AI tagged along. I guess this will be, you know, more the merrier. So yeah, come join us on Friday, November 21st, around 8 p.m. We will run or bus, if you don't want to run, to Sautel and then get food there. That's like there's a lot of good Japanese food over there, so it'll be a good time. And yeah, we'll meet at the Bruin there to start. And then one more thing. So this isn't really like an official event, but usually after Academy, like after 8 p.m. on Mondays and Wednesdays, the rest, all of us who are still around will like go to the hill together and get food. We like to call it cyber dinners. So if you want to join us for that, hang out with us. Yeah, okay. With all of that done, now please invite TS. He'll be talking about secure boot. So yeah.
All right. Hi everyone. So I'm TS and I'm an officer of like ACM Cyber, and today I'm gonna be talking about something called secure boot. So this is like related to like OS and how like to some extent like how the entire like hardware is booted up. So it's slightly complicated, and as a disclaimer says, I'm not very knowledgeable about it. I'm just trying to like introduce it to everyone because it's related to cybersecurity. And as I said, if you notice any errors in the content that I'm presenting, please feel free to correct me because like I'm very well, I want to learn like about what is correct. Anyway, so given the disclaimer, does anyone have any guess on what secure boot might be? Oh, sure. Yeah, lyric.
Like you're booting up a computer, like you do secure boot to like make it so like potentially unwanted programs don't like run along with the boot up. Maybe
Yeah, yeah, makes sense. It's true. That's right. Yeah. How about
Maybe
you?
making sure that like the code is what it's supposed to be and that people haven't tampered with it.
Yeah. So basically, both of you are correct, right? The idea of secure boot is that like you boot into a program or boot into like a kernel or whatever it is, right? That is like something that you expect that is verified. And we'll also talk about what it means to like verify kind of like a program using something called like a basically using asymmetric cryptography. Okay, so imagine the following scenario. So your company makes equipment, right, and develops firmware that runs on the equipment, right? And then do you want your customers to be able to like run whatever code they want on your device? And then why or why not? And so input, do you want people to run code on your device? Okay, yes. Okay, I mean probably maybe yes, but sometimes probably not. And then like the idea is like how do you prevent like people from just like easily running code that is not your firmware or your device. But also like later you kind of see that this may or may not always be the case. Sometimes you want to be able to allow for like firmware updates or things like that, and then you might have to make certain changes to like your entire like chain of trust in order to allow for firmware updates to be pushed properly. Okay, so as I was saying, generally you do not want customers or like random people to run like arbitrary code on your device because like it can like perform malicious actions and say that like, oh, you did it, or like gain access to like I don't know private keys that are stored on your devices that you may not wish to reveal, or like do other things. So perhaps with the help of cryptographic algorithms, we can ensure that only our verified firmware is running on like our device. Yeah. Okay, so the first target that we might think of is to target user-land programs. So, if you haven't taken like the OS class yet, you won't know the difference between like user space and like kernel space, right? And so most of the programs you use and run, they run in a permission space called like user-land. So that's where users' programs run. And in this permission space, you cannot interact with the hardware directly. Instead, you need to like go through, you have to go through the kernel, something called a kernel, in order to interact with the hardware. And the kernel provides an API for like your user space programs to interact with the hardware. And this is something called syscalls, yeah, system calls. So the idea of system calls is that you give control to the operating system to run something for you, and then it will return you what you want, right? And so, as I was saying, syscalls are the API that the OS provides to user-land programs. So examples syscalls are like dupe, which like duplicates a file descriptor, or like fork and exec, which I'll talk about later, or you can like do like read. It reads from like a file descriptor, or you can write. So these are just some examples, and there are like tons and tons of syscalls that are present within the specification. Okay, so what are some important syscalls in process spawning? Right, so if you took CS 111, certainly you have learned this, but just to kind of like go through it for those people who haven't taken or who haven't been exposed to it, there are two main important processes of syscalls. The first one is fork, and the second one is the exec family of syscall. Right, so what fork does is that it creates an identical copy of the current process with exactly the same state of the original before before it starts executing. So if you look at the diagram over here, after a fork, there's like a parent and then there's a child. And these two processes that are like forked will have the exact same like memory and the exact same things before they start running. Right? And then what can happen after that is that you can call exec on the child or whichever you want, and that will load in a new binary and start executing a new program. Right? So it starts with fork starts with one process and ends up with two identical processes, but exec starts off with one process and ends up with one new process, not new process, the same process running a new program. So there's fork and exec. So the idea is that whenever a syscall in the exec family occurs, you can do some sort of cryptographic verification, right, to ensure that the binary that's being executed is of what we expect, or a certain list of keys, right? Of signatures, I mean. So if verification fails, don't let the binary execute. So this is something that the kernel has to do, right? Because it's something that you check while in your system call, right? And so one example of such a thing is the very exact subsystem, and that's in NetBSD, but it's probably in some other OSs as well. I'm not very sure. But the idea is that you have a path to a file, and then you have some kind of fingerprints. Yeah, and so whenever you run a certain binary, it will check if the binary, the file, it will make sure that it's verified and is the correct binary before executing. All right, so here we have a quick pause. What does it mean to cryptographically verify a binary? So does anyone have any ideas? Okay, well, the idea is that we use asymmetric cryptography. So I'm not sure if you guys have heard of the difference between symmetric cryptography and asymmetric cryptography, but in symmetric cryptography, you use the same key to encrypt and decrypt your plain text and ciphertext respectively. But in asymmetric cryptography, different keys are used for encryption and decryption. So for example, in this, very common example, right? You see that let's say Alice publishes her public key, and let's say Bob wants to send a confidential message to Alice. What would Bob do? Bob will encrypt his message with her public key like this, right? And then since only Alice has her private key, only Alice can decrypt and read the message. Everyone else cannot decrypt and everyone else cannot read the message, and therefore this secure communication channel is set up in a way that doesn't require already a confidential channel that's set up to exchange symmetric keys. Okay, so signing is slightly different, right? Because it needs to flip the process. And so what needs to happen is that instead of encrypting, so-called encrypting with the public key, what you do is you sign with your private key, because that's the only you have the private key. So if you sign with your private key, right, everyone else who has the public key that you publish, right, will be able to read the signature and make sure that it's the correct value, right? So in this process, as you see, you sign the plain text and you get some ciphertext, and then everyone else, and then you send this ciphertext out there, right? And everyone else who decrypts this ciphertext can see that, oh, it's human readable, and therefore it's okay, this message has been signed by whoever the person is that released the public key. Okay, so how does cryptographic verification work in order to make sure that binaries are only binary keys that are verified are executed, right? So we start off from the start of the chain over here, right? We have data, which is our binary. So we hash the data. After we hash it, we sign it with a private key. After that, that gives something that's like both the data as well as the signature. And the signature will be in the form of a certificate, right? So after the signature is generated, right, how will we verify that that data is as expected, right? So what is the signature? The signature is like the signed hash. So what we need to do is that we need to hash the data again, right, to get the hash, and we also need to use the public key, right, to get the hash from the signature, and then we compare if like the hash from the data is equivalent to like the like the decrypted hash from the using the public key, right? Does this kind of make sense to everyone by using this process? So like if the data has changed in between like here and here, right, then the hash will be different, right? And because the hash will be different, like the hash will be different from like when you decrypt with the public key and like the resulting hash. So these two will be different if like someone has tampered with your data in between. So that's how you verify if like system has been like what you call it, like if the data is still as like the original. Yeah. So that's all good, right? Like, if the kernel can verify userland programs, like then no malicious userland programs can run. But well, is it possible that we've loaded and run like a compromised kernel? Or could it be that, like somehow our kernel got compromised? Right? And the answer is yes, because like the OS kernel is really a relatively large piece of software. And like even though there's like efforts to like make it like memory safe, like most of like the kernel is still written in like like in C or C++, which is memory unsafe. So you're not. Oh, and let's see. Oh, also you're not gonna be able to store the entire OS kernel in like read-only memory, right? So it could be corrupted or it could be like maliciously edited, like and when your like hardware or your thing is like out in the wild. So therefore the OS kernel is not likely to be stored on disk, and if the kernel is compromised, like this data can be written to arbitrarily. Okay. So like if you think about it, like a user LAN plus kernel LAN like kernel vulnerability can lead to the kernel being compromised, and this can also lead to like things such as rootkits being installed in the kernel, such that whenever when you boot up the kernel again, when you boot up your system again, like it persists and it's still malicious. So here are just some like vulnerabilities that have been reported to have been exploited in 2025. So it's just I looked at this like link. And so one example vulnerability is a heap out of bounds in net filter. And the other, so this vulnerability was discovered earlier, but apparently like they are still exploiting it till now. And another one is like a talk tool, the type of check time of use, which implies a race condition in POSIX CPU timers, and this leads to a use after free. So generally, these are all like heap-related vulnerabilities, and generally, like I haven't looked deep into these vulnerabilities, but the idea is that if you can compromise the kernel, you also are able to compromise user LAN, because like the kernel sits at one privilege level above like user LAN, and also like the OS provides both functionality as well as security to like programs that run in user LAN. Okay. So how can we then verify the kernel, right? Like what does that mean? And what is a privilege level above the kernel? So well, the bootloader is a software that will load the OS kernel into memory, right? And so can we verify this like bootloader in order to like make sure that the bootloader isn't compromised? Right? But then what if the bootloader gets compromised? And then and so on. Like what is before the bootloader? Like are we cooked, right? So I mean, obviously this has been like a problem at earlier stages, and we have kind of like have had solutions to it. So it's not completely cooked. But just to kind of introduce the boot process at a very high level, so we can split it into like the following 4 stages. The first is like a BIOS or UEFI stage, where it's like the very basic system. And then subsequently is the bootloader phase. So okay, the BIOS or UEFI, you load it from like non-volatile memory and you run something called like power on self-test. Like it just make sure that like the basic functionality is working. and after it does some like, detecting of like hardware devices that are attached, or like this that are attached. Then it chooses a boot device, and then in the mask, okay, it'll just, there'll be a bootloader in the boot device, and what will happen is that the bootloader, right, will be able to like do some things to be able to fetch like the kernel into memory, right, and that will be the kernel phase, and then the kernel phase will execute something called systemd, right? That's in Linux. In Windows, it might be completely different. The idea is that it executes systemd, which is the first process in user space, and the first process. So it always starts off with like one process, and then it always like forks and then exec. If everyone remembers like the model that I was talking about previously, right? So then after that, right, then there's some like stuff that are like system startup that I won't really get into. But the idea is that there's a whole boot process, and that in order to like secure the in order to if you think about it, like if the kernel, if you are scared that the kernel can get compromised, then we secure the kernel by like making the bootloader verify the kernel. Then what if the bootloader gets compromised, right? And so like there needs to be some kind of like starting point, right, that we can start to so-called like secure this entire chain of process. Yeah, so this is kind of like simplified, I would say. Like I also don't have that much knowledge about it, but we can think of it as like at the start of the chain, right? The main UEFI firmware is stored in read-only memory, and therefore like you control it. Right, so over here it says, basically most x86 hardware comes preloaded with like Microsoft like keys for verification. And so the firmware on these systems will basically be able to run like Microsoft signed binaries. And so like the reason why it's a Microsoft thing is because like I think Microsoft was the one that came out with this standard of like secure boot. And as you can see, like clearly my UEFI secure boot is not an attempt by Microsoft to lock Linux out of the PC market. So you definitely trust what they say. But anyways, so we see that the keys are preloaded into read-only memory in UEFI, and this will verify the bootloader, which will then verify your kernel, right? And you can like go on from there, right? So depending on your device, right, the link may not necessarily the kernel may not necessarily verify user land, because like if you are running like your MacBook or something, you want to be able to like run whatever you want, right? And so only in certain like kinds of firmware or like hardware, like routers or like security cameras, will there be like will the kernel, for example, verify every single user land program that runs? Okay, so yeah, so like what must everything be signed by Microsoft? Like let's say I develop a new kernel, like do I need to like send it to Microsoft, and then Microsoft like signs it and then sends it back to me, then I release it, right? Like that sounds like a huge like corporate trap, or like a like monopoly, right? So this is not the case, right? So what you can do is use something called a shim loader, okay? And that's what I'll talk about in the next slide. But basically, like a lot of like things like Debian or like Fedora or whatever like Linux like distributions or like kernels, they do this so that they don't have to keep like sending their things to Microsoft to sign and then release it. Like Microsoft signing should not be part of your CI/CD like release. Okay. Anyway, so what is a shim loader? A shim loader, at least in the context of secure boot, is a small loader, right, which is already signed by Microsoft, so it can run like at the UEFI stage, right? It's a pre-boot loader stage, and what it does is it embeds the keys of another organization. So for example, if I'm Debian, right, what I can do is I can sign my own binary, and so like I have this shim loader that's already signed by Microsoft, and then like I sign my own binary, and because like my keys are already embedded within that shim loader, right, I can sign my own binary, and then that will be able to run and boot properly. So hopefully that kind of makes sense. Like if yeah. So this kind of like lets you sign your own binary without requiring further signatures from Microsoft. They just need to sign that first like shim loader. Okay. So like aside from a shim loader, there's some like very like people who are like want to be very intimate with their computer, right? And then they want to like build the kernel themselves, right? So a key part of like the shim's design is to allow users to control their own systems, so in this case, like although there's an OS like distro like certificate authority key that's built into the shim binary itself, there's also like usually an extra database of keys that you can manage by the user that you can add to. And like technically, like you can think of this as an attack surface as well, but I haven't really looked into this as much. But the idea is to add functionality so that you can run your own like kernel, or you can like basically run your own kernel. And then keys can be added to or removed from the MOK list by the user. So yeah, you can sign your own bootloader, you can sign your own kernel, and then you can get the shim to load it. So you have like a lot of control over your computer, given the correct like functionality within the boot process. Okay, so I kind of like talked a lot about this like chain of trusting, etc. And I think there are some other aspects to it as well. But I kind of will just end off with talking about the last bits, or like certain factors that may be slightly relevant or like more relevant in the entire like secure boot like domain. Right, so the first one is like a secure storage of cryptographic keys. So like your cryptographic keys, like they can be leaked to like multiple like certain ways. Like what if like an attacker that has gained control of like the kernel, etc. Or will they be able to like get your cryptographic keys? Or what if like will your cryptographic keys be like reviewed easily, like while in a hardware like a serial bus or something like that. So the idea is that many devices now or hardware now have this thing called a trusted platform module, and it's a specific piece of hardware, a microchip, to store encryption keys. And these encrypted keys can only be decrypted by the TPM, right? And the TPM has a wrapping key or like some cryptographic key involved, where the private part is created in the TPM and like never exposed to any other component, software, process, or user, right? So like in that sense, it's like protected from the rest of like the system, if that makes sense, or being like transmitted or used by the rest of the system. I don't really know all of the details. Like technically, if you are trying to decrypt a private key and then you send the private key out of the TPM, that could also be like an avenue for compromise. But I just know that there's this TPM that does a lot of functionality. There's a whole like document on it, right? There's the main idea is to store and like store your cryptographic encryption keys securely. And aside from that, if you want to be able to like have some kind of like fallback or fail safe, such that you can change your private keys if required, there's something called like a one-time programmable memory, or an eFuse array, where you blow fuses in order to like set that memory, right? And the idea is that once the fuses are blown, the memory is written and it cannot be rewritten. So usually there are multiple slots in a single device, and what this can allow is that it allows for the change of keys if really required. So like if really like something happened and then like you need to send new keys out, like for some reason this like your chain of trust has like broken down in a certain sense and you need to send new keys out, this is possible. Yeah. And so aside from this, like aside from storing keys, the eFuse arrays also have this like functionality where they can prevent firmware reversion, right? Because it blows certain fuses to like indicate that the version is like incrementing, right? And this prevents like the version from decrementing, right? Because it's like not a string that's stored somewhere, but it's like fuses that are blown and they cannot be unblown. And so this prevents like a firmware reversion attack, right? That causes the system to run like a previous firmware that has like vulnerabilities that have not been patched yet. Yeah. So I kind of have like, hopefully given a pretty like wide-ranging summary of what secure boot is. And I think there's a lot already, and so we will not go deeper. But there is certainly much more to dig into, and there's like an entire like lots of like definitely lots of software developers who like work on this. But in conclusion, the secure boot is kind of like a security standard that's incorporated into the boot process to ensure that ensure the authenticity and validity of like system software at higher privileges than user land. And this is done through the use of cryptographic signatures, which I talked about earlier. And lastly, while powerful, secure boot isn't meant to like apparently to protect you against like physical attacks. So if like you're able to like physically access the device and like sniff the wires, basically for what I read online, secure boot isn't meant to protect you protect you from such attacks. Alright, so these are some resources if anyone wants to read, and any questions? Okay, yeah.
All right. With that, let me